Alright, today we're going to discuss industrial applications, which is chapter 5 in our book, and we're also going to look at some integrated manufacturing and just automation in general. Alright, so we want to try to design for good manufacturability. So we're going to look at some guidelines for when we try to select our robot and how these are applied. So the goal when we're designing products is to do it in such a way that we can maximize automation. So we want to try to minimize the number of parts, minimize obstructions so that the robot can get in where it needs to work on stuff. We need to come up with simplified fasteners, eliminate screws and springs when possible, because these are just kind of difficult to get robots to assemble. So use more things like tabs and snaps, and use common features on all parts whenever possible, and make them as symmetric as possible. So the design guidelines are features that are required for a robot to complete the given manufacturing task. So we want to try to increase speed. We want the robot to have a large work envelope. And we may have to have special sensors or tools for the robot to be able to sense something or be able to manipulate an object. Okay. But obviously the more features that are required is going to increase the price of the robot. So when we look at trying to pick what robot we need, we want to, match the robot to the task. Right? So there's some various different criteria that we need to kind of consider when we're trying to match the robot. Obviously, speed, accuracy, resolution, repeatability. Remember we talked about those the first week. All right, so we need to consider that. Is accuracy very important, or can it be a few millimeters off and still be okay? So all those sorts of things we need to kind of think about. How accurate does accurate have to be? What is our work envelope? What is our payload? What kind of geometry do we need? Can we get away with maybe a simpler geometry, which means that it's going to be a little bit cheaper, or do we need one of the articulated robots, which are usually the most expensive? And and that kind of goes along with the degrees of freedom. What degrees of freedom are required? Okay, so do we and as I mentioned before, the special sensors, do we need a vision system or some other kind of sensors? Do we need kind of special tooling? So these are just kind of all various aspects of a robot system or an automation system that we need to consider. So just as a rule of thumb here, they we kind of have this design guideline. So we have, like, over here on the left hand side, we have our accuracy, then the work envelope, the arm geometry, required axes, how many axes we actually need, our arm speed, our arm payload, whether we need the special sensors or special tooling. So we kind of group these up into 6 guidelines. And the idea is that when we're picking a robot, we want to try to pick 3 of the top. So when you look at a given task, You can say, well, I need all 6 of these. Well, you can have that, but it's going to drive up your price. So if we can kind of focus and say these are the 3 most important, then we can focus our selection on our robot and our equipment based on those, and we can maybe save a little bit of money by saying, well, some of these other things aren't that critical, so we don't need to purchase a robot that meets those. I mean, all the robots are going to meet them to some degree, but how exactly what degree we need is what we kind of consider. So here's just an example. We have eggs coming down a conveyor going to what's called a accumulation table. So they're just kind of moving around on this accumulation table, and then we want to have a robot that's going to pick up these eggs and put them in the carton. All right, and so so this is our task, and obviously we've got eggs which are kind of fragile. They're kind of a weird shape and stuff, so we might need a special gripper to pick them up and be able to manipulate them. Accuracy wise, we can probably have a little bit of slack there, because the general size of the eggs are kind of different sizes anyhow. So as long as we have the gripper designed so that it can pick up a few different sizes of the eggs, if they're off by a little bit, we can maybe design the gripper so it'll slide into place, and so we maybe don't have to be all that accurate. So maybe accuracy wouldn't be that high. When we try to set it down in the carton, usually there's a little bit of compliance there, so that it'll, because they're round, they're going to kind of slide down in there. So we probably have a little bit of leeway with accuracy. The work envelope, we might be able to get away with more of a spherical or cylindrical sort of robot with a work envelope, depending on how it's laid out. All right. Speed, I guess depending on how fast you want to put the eggs in there, maybe speed's important. If you want to detect that you actually did pick up the egg, you might need a special type of sensor to kind of pick that up. All right. So, but again, the idea here is that we've got these 6 general guidelines, and we want to just try to pick the 3 most important, and focus on that when we're selecting our robot. All right, so here's just another example. In this case, we have a conveyor bringing down blocks, but there's 2 different types of blocks. There's actually 50-pound blocks coming down during the first shift, and we're looking at maybe 5 blocks a minute, but during second shift, we're looking at 4-pound bricks, but we're looking at 10 of those a minute. And so, 50 pounds, if you're trying to pick up 50 pounds, you're going to have to maybe consider the payload, how you're stacking them, the arm geometry may not be all that important there, as long as you can pick it up from the one conveyor and set it properly on the pallet, or maybe, depending on how you're stacking it on the pallet, you might need an articulated robot. You're going to be trying to pick up 2 different types of blocks, so again, tooling is probably kind of important. Sensors, you could probably detect these blocks with some kind of light sensor or photoelectric sensor, or maybe a limit switch even. So sensors probably isn't all that critical. A lot of different ways we could probably pick it up with sensors. But again, these are just guidelines or thoughts that we want to think about when we're trying to select the robot for this task. Here's just one more example. We've got some polished, it looks like it says Polish there, but it's supposed to be polished chrome wheels coming down. Now, of course, these are wheels, so they're symmetrical. There's cylindrical, or they're round wheels, so you may need some special tooling to pick them up. You're trying to do 1.5 a minute. That's pretty fast, so speed might be an issue. Doesn't say anything about what the weight of them might be here. Payload might be an issue. All right, so again, these are just kind of some ideas here to at least get you thinking about, well, what's important or what's not important. Okay, and so we just want to pick the 6 that are most important. All right, so another way when we're selecting robots is, they're basically classified into application groups. And so there's 4 major application groups: assembly, non-assembly, general purpose, and mobile. All right, so assembly robots, usually assembly is a very difficult task. It needs high accuracy, high repeatability. And so there's certain robots that are focused for this task, and so those robots actually, a lot of them fall under a acronym here, DFMA, which stands for Design for Manufacture and Assembly. So they're saying that this robot was designed specifically for this application. All right, so as I mentioned, we need excellent repeatability. They're going to, of course, have to probably be fairly rigid and strong. And I do have a link in here that you can follow and just kind of watch on this robot here. Follow this link, and it shows you a pretty nice example of an assembly robot. All right, non-assembly has 2 main subcategories: painting and welding. And again, I've got some links there. You can click on those, open up these slides yourself, and click on those, and you can watch those videos, one on painting and one on welding. All right, but that's the non-assembly classification. And then we just have a more general purpose classification, which is general material handling, packaging, pick and place, palletizing, those sorts of tasks. And then the mobile robot. So there's a whole line of mobile robots coming up, and I'm sure in the future as we progress, we're going to see more and more and more of these. So the commercial class of these, of course, we have the vacuum cleaning robots and things like that. But for the commercial, when we look more at a commercial sort of application, we have automated guided vehicles. And I'm sure you're hearing about how they're trying to automate trucks for delivery, or just even cars. Google and Tesla both have done a lot with like automated driven cars and mobile robots. A lot of military applications for mobile robots. There's a lot of robots they're looking at for like inspection type tasks, especially like of bridges. A lot of these very large bridges, they need a lot of inspection and stuff, so they're looking at kind of like them Roomba vacuum cleaner sort of robots that can actually just move along the bridges and inspect for cracks or corrosion and things like that. All right, so this slide just kind of groups the 4 in there, just kind of labels a couple of primary aspects within these applications. All right, the next topic I want to address is called CIM, or Computer Integrated Manufacturing. Again, that's Computer integrated manufacturing. And this concept has been growing for years. I mean, it's been around for a very long time. I mean, even if you go back to the old paper days, a lot of this is just keeping track of, what is your raw materials coming in, what is your production rate, how much material do you have, and sitting there waiting to be shipped, and all just kind of all aspects of manufacturing. But as computers started becoming cheap, of course, they started tracking this information with computers. So, and this really isn't addressed in your book in chapter 5 too much, but I want to just address it right here because it's, like I say, it's becoming more and more important as we get into the Internet of Things. I'm sure you heard that buzzword IoT, or Internet of Things. And so this computer integrated manufacturing is actually evolving into what some people have termed Industry 4.0, or the Industrial Internet of Things, where we're tracking everything that's happening, all the way to the point that the robot is tracking how many items it's picked up and moved, how when's the next time it needs greased or needs replacement. Maybe it's tooling or something, it wears out after a certain amount of time, so it's actually tracking itself. Hey, I've got only another week before I need this tooling replaced, or something along those lines. So CIM, again, computer integrated manufacturing, is really growing into this concept of the Internet of Things, so that the fact that the robot schedules itself to have it shut down for repair, or for grease, or not repair but preventative maintenance type tasks, and grease and whatever else that you might need to do to the robot. All right, so but to do this, if you wanted to start, if you're kind of a company and you don't really have any automation, and you want to kind of incorporate this idea of computer integrated manufacturing, you need to basically do 3 things to get this implemented. So the first thing is assessment, and then simplification, and of course then the implementation. So, and again, this idea of CIM, or computer integrated manufacturing, is we're looking at everything from shipping, from materials, raw materials coming in, to the finished product going out, human resources, the people that are available, maintenance people, if you're going to have to shut down so often for preventative maintenance type things, accounting, manufacturing. So all of this is being integrated. So the first thing we need to do is our assessment. So we're going to look at what we're doing now and how we're doing it, and just kind of document it. All right, you need to document it. Some companies have really good documentation. This is how you go about doing orders. This is how you go about doing various aspects, then they have very good documentation. Others, maybe they need to do a little bit more documentation. Honestly, it seems like most companies could improve their documentation. Even the ones that have really good documentation, there's always areas where they can improve. So you want to look at everything you're doing, try to document it all the way along the line, again, because we're looking at everything from human resources, accounting, the actual manufacturing, the maintenance, engineering, inventory, all those aspects. So we need to assess it. We need to look at as part of the assessment, we need to look at the technical ability of our current workforce. Maybe they need some training. we need to look at every aspect of the production, how we move the product, how we go about hiring people, how our receiving and shipping is done, and what our spare parts inventory is, and all, just everything that you just want to look at everything that there is there. All right. Now, a lot of times there's a lot of people at a company that are like, we really need to automate this and to do this computer integrated manufacturing. But then there's other people who are hesitant to do that. And a lot of times some of these people are up in higher management and they don't want to do it, and they give various different reasons. So some of the reasons that we might see that they're opposed to it, or at least hesitant to do it, is lack of in-house expertise. They feel that they don't have their employees don't have the skills necessary to do this. Sometimes people just don't understand the benefit that they would obtain from that. They don't have proper planning, or they lack the vision. Inadequate cost justification methods. So they're when you're trying to justify, well, if I'm going to automate this, I am going to have to spend some money for the automation equipment, and how do we justify that? And some of that goes back to the assessment. If we understand what we're doing now and where our costs are involved now, we can help kind of alleviate some of that. So, all right. So after we've done the assessment, then we want to perform simplification. So we've looked at what we're doing, and before we try to implement some kind of automation or CIM, we want to remove as much waste out of what we're doing now as possible. I mean, there might be that sometimes you pick up parts and you move them over into storage, and then you pull them back over a week later or something, so they've just kind of been sitting there for a while. What's the point of them just picking them up, moving them, and storing them, and then having to move them back and send them down the rest of the line? Can we just eliminate that section of it? Any sort of things that we can do is, that we're doing is everything that we're doing adding to the value of the product, or is it just costing us time and or money and not adding any benefit to our product? So we want to analyze any waste and try to remove all of that as we go into the implementation phase. All right. And the other thing is, part of the implementation, obviously implementation, we're setting this up and getting things working using this new computer integrated manufacturing technique and tracking what's happening. And so one of the things that we want to do as part of this implementation is referred to as a benchmark. So we want to kind of record how long it's taking, and then how long like each thing's taking, and what our inventory is, if there's any setup time involved, what that is. What about our quality? Are there's parts that get rejected and then we have to send them back and reprocess them, or maybe they just turn out to be scrap and we can't use them at all? All right. And so we want to try to document all this and set it as a benchmark, so that we can come back later and compare after we implement this and see whether, it really does justify the cost and time and effort we put into it. All right. So here's just kind of an example of a pump manufacturer's performance. They did their original baseline, and they determined that it took 18 weeks to basically get 4 turnovers of their inventory. and 13% of that turned out to be scrap, meaning that, uh, at the end of the line, it turned out that the pump was no good, and they just had to scrap it. 45% was found to be good the first time. So this means, like, you had to send back like 32% of it. Well, you sent back 55% of it went back and had to have something reworked. And then out of that stuff that was reworked, a total of 13% of that still wasn't good enough to be sent. So, and they were also using up to 1,200 square feet of floor space. All right. So after implementing some of these, some various things that they identified here as part of the computer integrated manufacturing, they after 1 year, they were able to reduce the cycle time down to 6 weeks and double the number of inventory turns and reduce the scrap, increase the number of parts the first time around so you don't have to rework nearly as much, and also reduce the floor space. But then so at this time, we've reevaluated after the first year, and we after making changes and applying these changes that we identified, and definitely improved our product and our efficiency. But there was still room to improve. So after another 6 months, we reevaluate, and you can see that we actually got the cycle time down to 1 week, and inventory turns up to 48. And so this was actually an example from a true company here. This was out of the Reg book, Introduction to Robotics. This is where this table came from. But this was actually, a real company that and showing their improvement. All right. So the last thing we want to just kind of address is just factory automation. So if you remember, let me jump a couple slides ahead here. If you remember, the first week we talked about the 5 different types of production. And so one of those was what we called project. Okay, a project could be a bridge or a building. It was usually a one-time sort of thing that was unique. And so it doesn't necessarily lend itself to automation very well. And then we kind of talked about the job shop, where the job shop, you get maybe more than one of these things that you're going to do, but it's not a large number. Then we talked about the repetitive jobs. Once as you start doing the same sort of jobs over and over and over again, then automation and robots really start coming in and helping justify their cost. And so we had the repetitive jobs and the line jobs. And then way up here at the top, then we had the continuous job. So continuous type job is more of a dedicated automation. And so that's kind of what we're looking at here is 2 types of automation. The one is the fixed, which was listed there as continuous. And so that doesn't necessarily have a lot of need for actual robotic arms and that type of use, but definitely geared toward PLCs, programmable logic controllers, and things where you've got the material coming down a conveyor and you're processing large amounts of the exact same product. And then there's what they call the flexible, which the line and repetitive fall into for the most part. All right. And so just kind of as a repeat, project is not necessarily applicable to robotics. All right, but however, in a large project, there might be parts of it that are applicable to robotics. So, the whole thing itself is not, you can't like build the whole thing with a robot, but there are things like welding. A lot of times, if you're doing a lot of repetitive sort of welding, like if you're building a bridge and you have to, weld the girders together or various things like that, then there are areas within that project that you may actually be able to do a lot of robotics at. Similarly, job shops don't necessarily apply very well to robotics. The repetitive and line apply the best to a robotic work cell, and then continuous is just hard automation thing. So when we look at this slide here, notice down here at the bottom it says production rate. So as our production rate increases, right, and then our volume of parts, our actual number of outputs increases, that goes up this line, more toward the continuous. All right, so the project is down here with low production and low volume of final product. Like you built a bridge, you built one bridge, and it took quite a while to do that, right? But again, every bridge is unique. All right, and you look at a lot of bridges like on a highway or something, and you're like, well, this bridge looks just like the other, and that's true to a lot of degrees, but yet it's in a unique place. So the way it was actually, it's got the length of it or the height of it, the foundation of it, all of those sorts of aspects are unique to where that bridge is located. So there's, for project sort of applications, there's always at least some uniqueness to it. Now this slide looks almost the same, but what's different on this slide is the variety of the product down here. So again, as the variety increases, like I say, with a bridge or something, even though in general, there's a lot of repetition on bridges of how they're made, but where they actually go make them unique to some degree. And so, as your variety increases, you get down more to the project or job shop sort of application. All right, so when we apply flexible automation, all right, the idea here is that we want to be able to adapt to engineering changes in a part very quickly. All right, and so we're kind of in that repetition or line sort of thing. And a great example of this is cars, where a lot of automation is done with cars, and yet when you look at a car that's being built, and some factory might be making 1,000 cars a day, yet each car has, even though it might be essentially the exact same car build and most of the parts are the same, there's uniqueness to it. So they have, this car might have a sunroof, and the next car doesn't have a sunroof, or and the color of them are different, and this one maybe has a big fancy stereo, and the other one's got the cheap stereo. So there's little bits in there that make them unique. All right, so we need our flexibility in our automation here. And so we have these two concepts here: flexible manufacturing systems and flexible manufacturing cells. And the idea is that it's flexible so that it can be it's doing automation, and yet it can handle different parts. It can handle some variation in there. Okay, and of course we got to have our computer integrated manufacturing in there so that we know, what goes into this particular car. I've heard that the Corvette plant is when they build Corvettes, every car coming off the line has already been purchased. And if somebody's going to go buy a brand new Corvette, they're going to make sure they get the color they want, and they get, if they want a sunroof, or they want a convertible or whatever, they've already ordered it, so they've already ordered all those different pieces and parts. What type of wheels are they going to have on it, and which stereo system is in it? All that, you get the V8 with or without the turbocharger, or what are you getting in that? So you need that computer integrated manufacturing so that you're tracking and saying, yes, this is what, this is that car. It gets the color blue. It's a convertible. The next car is going to be a yellow Corvette, and it's going to have a hard top but with a sunroof, and all those little aspects. We need to know which car is getting which. Okay. And so the flexible manufacturing system is just kind of talking about the entire system, and we're going to kind of build that up with smaller work cells, or flexible manufacturing cells. All right. So like a CNC machine, and robot loading it would be a work cell, a flexible work cell. Okay. So each work cell, flexible manufacturing cell, is the building block to the complete flexible manufacturing system, FMS. Okay. And so, again, as we I keep coming back to this, right? So we have this dotted line around this graph down here, kind of, and you can see like the job shop is kind of in this dotted line, and the continuous is kind of in the dotted line, but all the things are kind of maybe sticking out of it a little bit. But one of our goals is to try to get it so that as much as possible could be inside of this box, where it can be automated as much as possible, and therefore improve efficiency and production rates. Okay. All right, so that's pretty much it for the flexible automation.